Well, I'd like to thank you all for sacrificing your, your Friday to come in to listen to my talk. Let's see. Today, what I would like to talk about is a slightly different topic. So the last two lectures, I sort of began by talking about point location and kind of general geometric algorithms. Yesterday I talked about the well-separated pair decomposition and the idea of geometric approximation. And I'd like to talk about another geometric structure today, the Euclidean minimum spanning tree. And in particular, I want to talk about an approximation algorithm for this problem. And I'm going to describe sort of two different algorithms. One is a classical, one of the oldest algorithm for this problem, and the other one is a very recent result, probably I guess dating from the last year. Okay, so let me begin with some definitions. Although I guess Wolfgang talked about the notion of the minimum spanning tree yesterday. So we're given a set of points in d-dimensional space. The Euclidean minimum spanning tree is the minimum spanning tree of the complete graph, where the edges are weighted by the Euclidean distance. So given this point set over here, this would be an example of what the Euclidean minimum spanning tree would look like, or EMST. Okay? Now, although you know that you know that minimum spanning trees can be computed in roughly n log n time, the n log n in this case is the size of the graph, which depends on the number of vertices and the number of edges. So because this is a graph over the complete graph, right, in this case the size of the graph would be n squared. So the natural running time would be about n squared log n, and it turns out if you want to compute EMSTs exactly, the running time is going to be about n squared, perhaps minus some, in this case it's minus 1 over d. So this is barely better than quadratic. So for this reason, it's of interest to consider approximations to the EMST. And in the example, I don't think you can really see it here, but here's an approximate EMST, here's an exact EMST. You'll notice that some edges, for example, this edge in the exact EMST is not here, but some other edge has been put in. And I guess, this length was about the same as this length. Similarly up here, this edge is not present down here, but some other edge of roughly the same length has replaced it. Okay, and the idea is that by computing the EMST approximately, right, you should be able to achieve greater efficiency. And that's the objective of this talk here, is to talk about how we can compute EMSTs approximately, but with running time that's closer to linear. Okay, and the exact definition is you'll be provided with a approximation factor epsilon, and I want to compute any spanning tree, but the weight of the spanning tree should be at most 1 plus epsilon times the weight of the minimum spanning tree. By the way, I will come back later on the talk to talk about the idea of what do you mean by an approximation. This seems like a very natural way in which to define approximation for the problem, but I should mention that there's actually a couple different ways of approximating the EMST. And I may return to this particular definition later on. This is a very natural way of defining approximation for EMSTs, but it's not the only way. Okay, so let me give you a little bit of history. So with respect to exact algorithms, there's a very well-known result in this area. Actually, this result by Andrew Yao was interesting because it actually introduced a number of ideas that have since been used in approximation algorithms in geometry. And the running time, again, was basically essentially quadratic, very, very slightly less than quadratic. This was improved to n squared 1 minus 1 over d. D, remember, is the dimension. Approximation algorithm. So the first approximation algorithm dates from 1991 and is basically of the form n divided by epsilon raised to the d. I'm using this notation O tilde here to denote the fact that I'm concealing logarithmic factors. Okay, Callahan and Casaraju. So you'll notice here that the dependency on epsilon, in fact, this is going to be very important in my talk. The dependency on epsilon is the power grows, notice, exponentially with d. You'll notice in this later result by Callahan and Casaraju in 97, they reduced the exponent to d over 2. Okay, and in particular, what much of the work has to do is how, basically the n term is going to be the same. I don't know why I put the log in here. I'm hiding the log factors. But the epsilon term is the important term here. Because this is the idea, you want to create the value that's as small as possible. Notice in both cases it depends upon d. And you might say, well, is the dependence on d important here? And there's an interesting fact that if you're interested in just computing the weight of the triangulation and nothing else, you can actually do much better. So Chazelle and a number of other authors have shown that for a general graph, I can compute just the weight, not the actual spanning tree, in time that is proportional to the average degree of the graph and sort of if I look at the ratio between the highest weight and the lowest weight in the graph. So notice this has no dependence even on n. Okay, so in particular you have no hope of outputting the entire MST. Okay, it just tells you, a number, 73. This is the weight, roughly speaking, up to epsilon of the spanning tree. And there were some papers by Chumai and others, Chumai and Solar among others, who have shown that that you can solve this in a geometric setting. This one has the epsilon dependency looks very similar to the value here. It's essentially quadratic. Remember, this would be 1 over epsilon to the power of 2 with a small term depending on d. And this was later improved in 2009 to eliminate any dependence on the dimension. So epsilon to the negative 7 times n. This works in any metric space. And so there's an interesting contrast here. I'm going to talk about this later, but the contrast is that algorithms that actually produce the minimum spanning tree have dependences on the dimension itself. Algorithms that just tell you the weight of the spanning tree seem to be able to avoid this fact. What I'm going to present are two results. I'm going to present a very simple algorithm that basically the algorithm that achieves the time of roughly 1 over epsilon to the d due to Callahan and Casaraju. So Callahan and Casaraju essentially made a modification of Vijay's original algorithm. And I'm going to also discuss a new algorithm which avoids the dependence on the dimension. So instead of having 1 over epsilon to the d, the dependence is going to be 1 over epsilon squared, irrespective of the dimension itself. So in other words, the important with this result is that the epsilon dependencies do not increase exponentially with dimension. And this, by the way, is a very recent result of mine and Sunil Arya. So let me talk first about the very simple algorithm. And this is an algorithm that's based upon well-separated pair decompositions, which we talked about last time. So a little history here. So Vijay, as I mentioned before, presented this, I would say, somewhat complicated algorithm that was based upon quad trees with this particular running time, 1 over epsilon to the d times n log n. And at the time, Vijay did not quite... Let's say it was actually a very nice algorithm because at the time a lot of the ideas that come up in geometric approximations were not kind of developed at that point in time. In fact, this was one of the very early results of an approximate algorithm in geometry. Rupert and Seidel, about the same time, made the observation that as long as you can compute a 1 plus epsilon spanner, you can use that to construct the minimum spanning tree. In fact, that is the algorithm that I'm going to present here. You use actually the spanner to derive the spanning tree. Callahan and Casaraju sort of explain, in particular, that you can take Vijay's idea and express it in the context. If you remember from last time, we talked about how you can build a spanner using a well-separated pair decomposition. And they presented an algorithm that essentially just makes this link direct. That from the well-separated pair decomposition, I can actually get the spanning tree. The running time was the same as Vijay. Now they actually mentioned an improvement to this. They gave a more sophisticated algorithm which improves the exponent here. But I decided not to talk about this algorithm. This is actually a very interesting algorithm and uses some techniques that have to do with approximating distances in Euclidean spaces, which are actually quite nice, but there was sort of a limitation as to how much stuff I wanted to present, so I'm not presenting this one here. I'm going to present the simpler algorithm by Callahan and Casaraju. Okay, so let me remind you about the well-separated pair decomposition. To be well-separated, if they can be enclosed, well, for a parameter s, that's the separation factor, if they can be enclosed within balls of radius r, such that the separation distance is at least s times r. Okay? We mentioned the fact last time that if I give you an arbitrary point set and a parameter s, then I can build a set consisting of s well-separated pairs that covers all the pairs of the set, right? So for any pair here, there will be some well-separated pair, let's say this block here, that represents that pair. And in fact, this is a one-to-one thing. Every pair, there's a unique well-separated pair that represents that pair. And Callahan and Casaraju showed that given any parameter s, given any n-element point set n, that I can construct a well-separated pair that consists of this many pairs, s to the d times n. So again, if thinking of s and d as constants, you can think of this as being roughly linear in n, that can be built in output-sensitive time. So n log n, if you remember, n log n was to build the quad tree or the BD tree or BBD tree, whatever variant of quad tree you want to use. And the k represents the output time, the amount of time it takes to generate all the pairs, which is essentially linear. Okay, a couple of other facts that will be useful here. Remember also that every well-separated pair is represented very succinctly. So in other words, even though a pair might represent many points with many other points, I'm just going to represent that pair by just storing a link between two nodes in the quad tree. Or you can think of this visibly as for every pair of nodes in the quad tree of roughly equal size, I'm going to store a link between them if they're well separated. Okay? And if I think of notationally, if u and v are the nodes, let me think of p sub u as the set of points here and p sub v as the set of points here. I'm going to use capital P of u and capital P of v to denote these sets. And finally, that for every well-separated pair, I'm going to assume that I have a pair of representative points, p sub u and p sub v. And the reason I can do that is if I go back to the original quad tree representation, I can imagine that every internal node just selects one of its leaves arbitrarily to be sort of a representative point for this node here. And then when I go to the well-separated pair, I will just use the representative point for the associated node u. That'll be my representative here, and p of v will be the representative. You might think that maybe if I do a more careful job of selecting the representative pair, I could get a more accurate representation for the minimum spanning tree. For example, we'll see here that the better choice maybe for selecting this point would be actually to pick the closest pair between these two sets here, right? If I want to think about trying to minimize the edge length, rather than picking this pair of points, perhaps I should pick the closer pair. Although this is a very reasonable idea, the problem is computing that closest pair is going to take you time. And that time would then go into the time of your, computing your minimum spanning tree. So there's a trade-off to be faced here. You could try to pick up this point more intelligently, but doing so would increase your running time. So, in fact, we're just going to imagine that this point is just an arbitrary point. Okay, so let me describe the algorithm here. Again, this is the algorithm, I can think of this as Vijay's algorithm, but expressed in the language of well-separated pair decompositions, and this was given by Callahan and Casaraju. So let's suppose we start with a point set. Okay, I'm going to compute, let's say, a well-separated pair for this point set. I'm going to use this particular factor. Again, remember, there's always this, how did you pick this factor? Well, the justification for the factor would be as follows. Remember from last time that if you want to construct a T-spanner, then what you do is you build an S well-separated pair decomposition where S was equal to, I think it was 4 times T plus 1 divided by T minus 1. Okay? And in this context, what we're going to want is to compute a 1 plus epsilon spanner. Right? Remember, epsilon is the parameter, the approximation parameter for the spanning tree. And so if I think of this as being my value of t and plug it in here, right, what do I get? I get 4 times t plus 1, so that would be 2 plus epsilon, right, and t minus 1 would be epsilon. So this is the particular reason why I chose this value for s. So this means in particular that recall the definition of a spanner, that if I have any pair of points x and y, right, the length of the direct path between them will be xy. But this path may not appear in my well-separated pair decomposition, but there will generally be some path here, right, such the length of this path here is going to be, let's say the length of the path xy within my graph G is going to be less than or equal to, t times the direct distance between them. In this context, it'll be 1 plus epsilon times that. So I want you to think about this is sort of my target here. My target here will be to come up with a graph where every edge is going to be represented by a path whose length is nearly the same. So we actually just gave this algorithm last time, so I'll kind of pad through it again here. So remember, for every well-separated pair here, what I'm going to do is I'm just going to grab the two representative points. So let's say this point and this point was a representative point. I connect them. Okay, I'll select another well-separated pair. I'm not quite sure which one I'm selecting. You know, when I show this on my laptop, it's pretty obvious which one is. Okay, so it's this one and this one, I guess, I picked. So I selected the pair between those guys. Again, I select another well-separated pair. I selected a pair of edge between those guys. I just keep repeating this until finally, at the end of the day, for every well-separated pair in the original graph, I now have an edge that results from that. Okay, so there's a one-to-one correspondence between the edges in G and the edges of the well-separated pair. Then what I do is I compute the minimum spanning tree of this graph. Okay, so the time for this, of course, is going to be what roughly, you know, m log m, where m is the number of edges of the spanner. And I'm just going to return this graph as my final answer. Okay, so what's the running time? Well, the running time, again, if you think about running times for minimum spanning trees, is you take essentially the number of edges in the spanning tree times an additional log factor here. Actually, there's probably an additional log factor depending on the s. I'm just going to kind of ignore this. So what I get is, in this context, since s is blah, 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 s basically is growing as about 1 over epsilon, right? If epsilon I'm thinking of as being a small number, this is on the order of 1 over epsilon. So s to the d, this was the number of well-separated pairs, is going to be about n over epsilon to the d. And then I'm going to get a log n. So notice, if epsilon is not too small, right, the running time is very nice. It's looking like roughly n log n. But again, there's going to be some dependence. It's going to depend on how accurate the answer is. The more accuracy you get, the higher the dimension, the more you're going to pay for in the running time. Okay, and let me give you an analysis, very quick kind of a sketch of analysis. So, so observe, as I mentioned over here, that G is going to be a 1 plus epsilon spanner, okay, as described before. In other words, this property is going to hold. That for every edge that is actually in the Euclidean minimum spanning tree, and by the way, here's the exact Euclidean minimum spanning tree. So you'll notice that some of the edges that are in the spanning tree are not there. This edge, for example, is not present in the graph above. This edge here is not present in the graph above. But I want to claim that the weight of this tree and the weight of this tree are about the same. Okay? And by the way, don't take out your ruler. You know, I drew this by hand, so it might be that there's some edges that are, you know, not quite proper. But I wanted, this sort of illustrates the idea here. So let's think about why this is the case. So what I want to prove is that this graph and this graph have roughly the same weight. And to do so, what I'm going to do is I'm going to imagine, start with the minimum spanning tree. Okay? And let's replace every edge with its corresponding path in the spanner, right? For every pair of points, I know that there exists a path in the spanner, right? That is what's going to be the case. So let's imagine that I replace every one. So for example, if I replace this edge, well, this edge already appears in the spanner, so this will actually be there. And this edge, well, that edge also appears, oops, let me go back. This edge also appears in my spanner, so it'll be there. But this edge, that is the edge between these two guys, does not appear. But there is a path in the spanner, right, that goes up and around there. So let's put this guy in there. Now when I do that, notice that I put this edge already there, right? And the upper edge, this was already in there. And so the path that I've just added has now used this edge a second time. It's gone up here, and it's used this edge a second time, right? So this edge is getting counted twice, this one once, and this one twice. Similarly, if I go back, let's look at another example. So this edge here is not in my spanner, but there is a spanner path for this guy. The path went from this vertex down to the representative, followed this edge up here, and then came out here, right? That is the spanner path for this particular edge here. Okay, so again, these edges are in the MST, and they're just going to be representing themselves. Okay? But this edge is going to be used a second time for this path. And then I'm going to use this edge, actually this edge here in the spanner, and then I'm going to use this edge a second time. So when I go forward, again, this edge, I'm just going to use it for itself. This edge, I'm using it for itself. This edge is being used for itself. And this edge is being replaced by its path in the spanner. So I use this edge a second time, okay, that I've noted here. Then I follow this edge, and then I use this edge a second time. Okay? So this now is essentially an encoding of the EMST using the edges of my spanner. And notice what happens to the weight, right? Whenever I replace an edge here of some length, let's call it W, I'm replacing it with a total weight of 1 plus epsilon times W. So the weight has increased by a factor of 1 plus epsilon in the process here. Now notice this is not exactly, in fact this doesn't need to be a spanning tree. There actually could be cycles and other things inside of this graph. But the point is this, that the weight of that graph, even multiply counting the various edges that have been used twice, is at most 1 plus epsilon times the weight of the original weight of the minimum spanning tree. Okay? Now, if I compute the minimum spanning tree of this guy, the weight can only go down as a result, right? I'll eliminate this edge. If there had happened to be cycles, and that is possible, it might be the case that depending on how these were working out, rather than getting this edge counted, I might have added this edge. I could have induced a little cycle here. But again, the weight would have been at most 1 plus epsilon times the weight of the EMST. And then when I compute in this step the MST of G, the weight will only become even smaller still. Okay? So this is why the weight of the final MST of G cannot be any larger than the weight of this particular graph. And since this weight is already 1 plus epsilon times the weight of the spanning tree, then I get the desired weight. Okay? So this, by the way, is kind of what I've done is I've applied the spanner algorithm and then run the MST on it. And as I mentioned before, it turns out this spanner is not the only spanner you could do this for. In fact, any 1 plus epsilon spanner that you build, you can apply this technique of first build the spanner, then build a minimum spanning tree of the spanner. Okay, so I've given this first result here. What I want to do next is I want to present this more recent result, which, like I said, the main thing here is this improvement in the running time. So the key thing is that the epsilon dependencies do not grow with the dimensions. So let me, again, kind of go into this idea a little bit further. So, there's an interesting question here about, what is important when one studies approximation algorithms? Okay? In particular, when people look at running times, look at a running time like this. I have an n, I have an epsilon, and there may be, in geometry, there may be a dimension d. The sort of question is, well, what are you trying to minimize here when you try to minimize running times? I sort of have an assumption that I frequently use, which is something like this, that, the dimension d I always want to think of as being, let's say, a constant. I usually want to think of epsilon as being an asymptotic quantity. Okay, but I typically think of 1 over epsilon as being a number that's much less than n. So I think of, 1 over epsilon as maybe, if epsilon is maybe, 10%, 10%, 1%, 0.1%, right? 1 over epsilon may be a number like 10, 100, 1,000. Whereas I would like to think of n as a number that is potentially very large, right? N may be in the order of, hundreds of thousands or millions or something like this. And so the idea is there's sort of a two-phase thing. We want to minimize usually the dependence on n, but the epsilon dependencies are even more important. But as a consequence of this, I tend to think of, for example, log n as being a lower order term. And not everybody, would agree with this perspective here. A lot of papers, people would say, well, n is the most important term, and I must minimize all of the factors that depend on n before I minimize any factor that depends on epsilon. In practice, however, these logarithmic terms tend to be very small. Okay, it's these. The dominant term is almost always n, and secondarily, it's an epsilon factor here. Okay, so let me describe what the the basic background to this. So as I mentioned before, the epsilon factors of the algorithm I've just described, rho is epsilon to the 1 over d. The improved algorithm, which is, I don't know how practical it is, but it has a much better dependence on epsilon. But these have a significant impact on the running time, right? Again, if I imagine that I'm solving this problem in dimensions somewhere between 2 to maybe 10, right? Taking a parameter, even if I'm talking about a 10% error, raising that 1 over 10 to the fourth power or something like this, and this multiplying this times your running time, right? That's going to be a significant impact. So I would like to keep this quantity as small as I can. So I either have to deal with the fact that my epsilon factors are going to grow exponentially with dimension, which I don't like, or the alternative, remember, is I have these results by Chazelle and Shumai and others that essentially says, hey, if you just want the weight of the spanning tree and nothing else, you can do much better. By the way, the reason these algorithms are just giving you the weight is because they're using a random sampling process. They will just they'll sample a vertex and the local neighborhood, they'll sample a vertex in the local neighborhood, and by repeating the sampling and local inspection process, the claim is if you do this enough, you can actually come very close to estimating the weight of the spanning tree. And by the way, if you think about this, this is very surprising because a spanning tree, right, is a global structure, right? It has to be globally connected. And so you might say, how could I just look at a vertex and maybe the nearby, or a point and the nearby neighborhood of that point and expect to know anything about the global structure of the spanning tree? This is a very cool algorithm. I would recommend, if you're interested in, what paper should I read next, you should look at some of these algorithms for the spanning tree, particularly the Chazelle paper. It's a very elegant and simple idea. The Shumai and Solar paper, when you try to map this to the geometric setting, it becomes a lot of complexity gets added there. But the Chazelle paper is definitely, it's a very short paper, and the main idea is very easy to understand. And again, when you read it, it's kind of a, oh wow, what a clever notion there. Okay, so what is our recent result here? So like I said, recent, this is from way back in 2015. So here's the idea. We would like to compute an epsilon approximation. The running time will not depend on d, but we will actually not compute just the weight. We're actually going to compute the entire EMST. The algorithm is going to be a simple deterministic algorithm making use of basically quad trees, well-separated pairs. And like I said before, the epsilon factors do not depend on the dimension. Okay, so how does this algorithm work? Well, to begin with, I'm going to begin with an observation by Callahan and Kasaraju. So the first observation is every pair of a two well-separated pair, and I should say actually not really two, but slightly bigger than two, okay, will contribute at most one edge to the EMST. And let me give a proof of this fact. So I want to claim that if I looked at the final EMST, either there will be no edge going between this pair, or there will be at most one edge going between the pair, but there can never be two edges. There can never be two edges going between a well-separated pair if I have a separation factor that's 2 or larger. And like I said, actually the way I should state it is strictly bigger than 2. So 2.00001. I cannot have two edges. And why is that? Well, if you look at these, remember what does it mean to be two separated? Well, these points are enclosed in a ball of radius r, which means that every pair of points is at distance at most 2 times r from each other. So if I'm running an algorithm like Kruskal's algorithm, right, everything inside of here, all of these edges will be added, right, before I consider any edge bigger than 2r. So all of these guys are going to get connected to each other. All of these guys are going to get connected. They may not be connected to each other directly, right? The connection may go outside and come back in. But the point of fact is that before I ever consider this edge here, right, these guys will all be in a connected component. These guys will all be in a connected component, right? And so, well, excuse me, I'm getting ahead of myself here. So in that case, once this edge, if the edge is going to be added, and by the way, if it is added, it'll be between the closest pair. Once it's added, then everything will be connected. The second observation that they make is that, again, if I give you this very slightly bigger than 2 well-separated pair decomposition, that the edge that you will add will always be between the closest pair of points. And again, you can see this from the construction here, that these guys will be connected, these guys will be connected. If I'm going to connect these guys together, the best way to do it is always to take the closest pair. This is just what Kruskal's algorithm would do. Okay? So if, for every well-separated pair, I construct a graph G by joining the closest pairs, Okay? Then, in fact, I will actually get the exact minimum spanning tree. Okay? And remember that the size of the two well-separated pair is going to be 2 raised to the power of d. Well, if I think of d as a constant, then the size of the graph is just going to be O of n. So in other words, if I could actually compute these closest pairs efficiently, then I would have a very efficient algorithm. Now, the problem is going to be computing these closest pairs. And the way Callahan and Casaraju in their 97 algorithm come up with the improvement is they come up with a more efficient algorithm for computing closest pairs in well-separated graphs. But this is the important thing then, finally. So computing epsilon approximate closest pairs results in an epsilon approximate EMST. In other words, if I can't compute this exactly, then I will settle for an approximation to these closest pairs. Okay, here's another useful observation that we're going to make use of here. Let's consider a grid of side length S. So each one of these cells here has a side length of S here. Okay? Let's let M denote the number of grid boxes that contain at least one point of the set. Okay, so build a grid and then throw away all the boxes that contain no point. And let's let M denote the number of boxes that you get. Okay, what I'm interested in arguing about is basically what is going to be the weight of the spanning tree. Let me just show you the spanning tree. So here's the spanning tree that I'm interested in. And I want to argue something about the weight of this spanning tree. Okay? Now, I don't want to compute the actual spanning tree. What I just want to say is, well, just in terms of how many boxes you have, your intuition would be as follows. That if you've got lots of boxes, right, then it would seem that you should have more weight in your spanning tree. Okay, now how much? I don't know exactly, because the amount of spanning tree within a given box could be huge, right? If I put 1 billion points inside of here, the spanning tree would have to go all the way around. It could have a very large weight. But I want to claim that the amount of weight that you would expect to see in one of these boxes should be about S, right? Because S is the side length. Okay, now you say, well, wait a minute, that might not be true. I might have just 2 points that are very, very close together. The weight of the spanning tree could be much, much smaller than S. Okay, but nonetheless, I want to claim that the weight of the spanning tree is going to be about S times M, okay, and then, you know, up to constant factors. And again, you might say, well, wait a minute, why should that be true? You know, let me give you a bad example here. You know, this is of side length S, and maybe I put a point here, 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 and here. If I connect these guys together, right, okay, wait, there's something wrong here. This spanning tree has extremely tiny weight, but, you know, M is equal to 4. By the way, I probably eliminated something here, which is there actually should be a small constant here. It really should be, I wrote Sm minus C, but it's actually S times maybe M minus 2 to the D, or something like this, divided by C, because I have to allow for the fact that if M is extremely small, I actually will not have any weight there at all. But I want to assume that M is going to be actually strictly bigger than 2 to the D here. So let me give you a quick sketch of this result here. So here's the way we're going to prove this. Within a given pair of neighboring boxes, right, I can't say very much about the weight. But notice once I get beyond this, once I add, you know, a box that is somehow not connected to one of these. So let me put a box down here, for example. Okay, notice now if I have any point in here, it's going to have to make a connection. Okay, and that connection length, right, is going to have to span between multiple boxes, and is going to have to be of a length at least S. So to get this idea, what I'm going to do is I'm going to color. Do I have a coloring here? There actually were colors here at one point in time. Okay, so pretend that this is colored blue, this is colored blue, this is colored blue, this is colored blue. Gosh, can you see them at all? I have to change my colors here. Okay, I think it was this one, and this one. We're all colored blue. Okay, what I'll do then is observe the fact that if I color the boxes, there will be 2 to the D colors such that every pair of colored boxes are separated from one another. Okay, so these actually are at the end. So if you were wondering which boxes are colored, okay, those are the boxes that were colored. Oops, sorry. Okay, good. And then observe that right, I've I've reduced the number of boxes, but the number of boxes now, at least one of the color classes has to have M over 2 to the D boxes. Okay, let's assume that in fact M is big enough that there's at least 2 boxes here. And then I have to make a connection, therefore, between 2 of these guys. Well, every time I connect 2 of these boxes, I have to pay at least the length of a box, right, to form this edge. Similarly, between these, I have to pay at least a length of S. So if there are this many boxes for this minus 1 edges, I have to pay a cost of at least s to connect these guys. So therefore, again, for m sufficiently large, the cost of connecting these boxes is going to be s times m. Okay? Questions about this? This turns out to be a very handy thing because it means that I could have a billion points out there, right? Or, as Jason would say, a zillion points, right? I could have a zillion points there. Invent any number that you like. But as long as I can count the number of boxes, I can very, very quickly come up with an estimate on a lower bound for the minimum spanning tree. The spanning tree could be much higher, but it's not going to be lower than this. And that's going to be important in the algorithm. Because again, it's easy to count boxes. It's harder to actually count the weight of the spanning tree itself. Okay, so here's the way the algorithm is going to work. And it's not very complicated. What I'm going to do is I'm going to compute a well-separated pair decomposition. Again, the separation factor here, even though I'm going for an epsilon approximation, the separation factor is just going to be a constant. Okay? So the actual well-separated pair decomposition is just going to have n pairs in it, right? Maybe 2 to the d times n, but just n. Okay. Each box, remember, stores a representative point. And for each well-separated pair of the decomposition, I'm going to do the following. Okay? Let me blow this up so I can see all the points inside of that box there. Okay, first off, what I'm going to do is I'm going to start subdividing this box. In fact, I'm going to do this in parallel for both A and B. So I want to think of this as a breadth-first process. Start with the 2 boxes, split them both. Okay, so now I have 4 sub-boxes. Keep just the non-empty boxes. So split them again in parallel. Keep splitting them until one of 2 things happens. So let S be the box size. Keep subdividing until one of 2 events occurs. Okay, so subdivide, subdivide. Again, just keep the non-empty boxes. Subdivide. Okay, one of 2 things will occur. Either the box diameter will become very small, and small for me will be epsilon times s. Okay, that is a good event for me. At that point in time, I'll just stop the subdivision. The second event that I'm interested in is if the number of non-empty boxes becomes large. Okay. In particular, if the number of non-empty boxes here is, I think there was actually some coloring. Boy, oh boy, the colors are just not coming out. Yes. Okay. There was a nice little color about these things. If the number of non-empty boxes grows to at least c over epsilon, then I also stop the decomposition. Okay. I want to claim that these 2 things are good. Actually, do I say anything about it here? Well, I'll say something in just a minute as to why it is. But let me sort of provide you with some intuition as to why both of these events are good. Small boxes are good because it means that if I compute a closest pair based on these guys, right, it means that I have a very accurate notion of distance, right? Remember that, well, as I've drawn it, there's only 1 point in each box, but there could be many, many points in a box, and I'm just going to pick an arbitrary one. So that means that I'm not going to get the closest pair exactly. But if the box is very small, it's okay because I'm getting a good approximation to the actual, I'm going to take basically one of these guys and connect it. If the number of boxes is big, that's also good for me because it means I have a lot of weight here. And if you think about it, because we're approximating the weight, if I have a lot of weight present in my spanning tree, that's a lot of weight that I can charge my error against. Okay, so this is the intuition of why these 2 conditions are useful. So what I do next is the following. Remember, I've got all these boxes over here. I'm going to find, basically by just brute force, right, the number of boxes, right, there's at most 1 over epsilon boxes here. So I'm just going to pairwise look at all the pairs of boxes here, all the pairs of boxes there, look at all of the representative pairs. I'll just take the closest representative, right? And this seems extraordinarily stupid. I'm just looking at all pairs. You might say, couldn't you do better than that? Couldn't you design a better data structure for finding the closest pair of representative points here? We actually could not do this. I mean, the problem is, well, this is very simple, but improving this seems to be difficult without increasing the epsilon dependencies. Okay. So what I'm going to then have at the end of the day is I'm going to have a pair of approximate nearest neighbors for AI and BI, and I'm going to use that to basically to create an edge for my graph G. I'll add this edge to the graph G, and then at the end of the day, I'm going to compute the minimum spanning tree. So same as before, right? Every well-separated pair gives me an edge. Okay? I accumulate all those edges, and I then just compute a minimum spanning tree on those guys. I should mention, by the way, that this graph that I produce here is not necessarily going to be a spanner. Okay, and this to some extent is how we get a better improvement in running time. And you might say, why is it not a spanner? If this was the case, it actually would be a spanner. But if we terminate because of this condition here, the graph may actually fail to be a spanner. So this is not quite the same as the previous spanner-based approach. Okay? Okay. So let me give you the approximation analysis for this. By the way, let me first go back and just ask whether the algorithm is clear. So let me outline this again. You start by building a very coarse, well-separated pair decomposition, okay? Independent of epsilon, just a two-factor thing. You look at every pair of well-separated pairs, right? And I want to get an estimate I want to find a good choice for the closest pair, okay? So I just split until either the boxes are small, good. Small boxes are good because good approximation, or lots of boxes. Okay, lots of boxes, good, because lots of boxes means it means your spanning tree is very bushy, right? You have lots of leaves and branches in your spanning tree. That's good because if I make a mistake, I can charge my mistake against all of the bushiness that I have there. Okay, so either of these two conditions is good. Again, the number of boxes in any one of these guys is at most 1 over epsilon, so I just compute the closest pair, every box over here against every box over there, look at the representatives and take the closest pair. Okay? And then that gives me a pair of points, one per well-separated pair, add them to your spanning tree and compute the minimum spanning tree. Okay? Question?
Yeah, why do you have to look at all tests? Can you just compute the Voronoi diagram?
Yeah, this is the problem. The problem, remember, is we're trying to avoid the epsilon dependencies. And all intelligent techniques for computing better things, I'm going to get a 1 over epsilon to the d or a 1 over epsilon, or I'm going to get, yeah, that's right. Whatever I'm going to do, it's going to kind of, the dimension is going to come and kill me at some point in time. Yeah, that's the right. So the problem is to keep the dimensionality out of this. You got to be really stupid. But if you can think of something that's, not so stupid, I'll be happy to hear it. Yes. Okay. Yes. Okay, so here's the analysis. So there's two reasons why we could terminate the search, right? Box diameter is small, lots of boxes. So let's think about this. Suppose that I get down to a point where the box is actually very, very small in each one of these cases. Well, what do I know? Remember that the separated pair says, well, these guys are of radius r. They're separated by distance s times r. Well, let's say I normalize. Suppose I say this is about radius 1. This is about radius 1. This distance here is going to be about radius s. So this box is going to be of about size, right, epsilon times s. This distance is going to be about s, right? This is the two-factor approximation. Again, I'm ignoring kind of the constant factors here to make it easier. But since the box diameter is s, that means the absolute error is going to be about epsilon times s, which is going to be about epsilon but by the distance between these two boxes here. And so therefore, if I look at the relative error, I'm making an error of about epsilon, right, times the distance between the 2 points. So if I look at the ratio of the epsilon times the actual length of the edge I'm adding, the relative error is going to be about an epsilon here. So in other words, this edge is a good approximation to the actual shortest edge. Okay, the other possibility is suppose that the number of boxes is high. Okay, well, when I finally decompose these, I'm going to have some diameter of the boxes. Let's call that delta. Now again, delta could be a lot bigger than epsilon times s. Okay, so I'm drawing this box as fairly big. It's not a good approximation at this point in time. Okay, the absolute error is going to be proportional to delta, right? Because since I'm looking at the closest pair of points in boxes, I'm just choosing a representative point. The two representatives I pick are not going to be the closest in these boxes, but the error is going to be about the diameter of the box. That's the absolute error I'm making. Okay? But remember, if I apply my previous lemma, the lemma said, hey, if you know how big the boxes are, and you know how many boxes there are, you know what the weight of the spanning tree is, right? A lower bound. So by this bound, remember, we know that the boxes have diameter about delta, right? That was sort of our side length before. We know there's c over epsilon of these guys here. Okay, and let's suppose, remember there was a constant in that lemma there. Well, I'm just going to choose the c in this context to cancel out the c there. And so the weight of the spanning tree within here is going to be about delta over epsilon. So again, what's the error that I'm committing here? You're committing an error of about delta but you're charging it against, right, a weight of the spanning tree that's about delta over epsilon. So if I look at the relative error now relative to the entire spanning tree, it's the ratio of, right, this divided by this. Well, that's just going to be epsilon. And again, it's amortized over the entire box. So the good news here is this, that rather than charging my error against every individual edge, what I'm doing is I am charging against sort of the nearby weight of the spanning tree. And this is the new insight, I guess I would say. It's not a big insight. It's a very small insight. But this is sort of what differentiates us from the algorithm by Callahan and Karsaraju. Now, you might complain at this point. You said, hey, wait a minute here. You're charging the weight of this edge against this spanning tree stuff here. But this is just one of the well-separated pairs that is using this guy, right? There's a well-separated pair out here, out here, out here, out here. Those guys could all be charging the same, the same branches of the spanning tree. And that would not be good. So there is an issue here about multiply charging. So let me see, how much time do I have? I got a little bit more time. So let me explain, by the way, the following. That the paper that describes this consists of sort of two parts. There's a couple pages that describes the algorithm, which is very short. And then there is this long 15-page section that does the analysis, okay? The 15 pages is basically, well, maybe it's not 15, I'm not quite sure. But there's a long explanation, and it deals with the multiple charging issue. The multiple charging issue is not an easy thing to discuss. There's multiple charging going on at various levels. There are multiple charges that are going on at sort of one level of the tree, and there are multiple charges going on because of the hierarchy of the tree. And dealing with all of this is relatively messy. So I'm going to give you a very simplified, explanation here. If you're not satisfied with this explanation, well, I'll be happy to discuss this with you further. But we are multiply charging edges. And so there's sort of two reasons for this. Yes. The problem is that edges may be charged twice. One way to deal with this, by the way, is we had two cases, 1 and 2. If I go back to the previous thing. So this case is charging the edge. This case is charging these edges down here. I can deal with that, though, by the fact that I basically will reduce my epsilon to epsilon over 2. So the type 1 and type 2 cases, I can say, okay, there's an epsilon over 2 being charged in one case. There's an epsilon over 2. The total charge is going to be about epsilon. That's kind of a minor thing. The more difficult thing, though, has to do with charging the edges within these well-separated pairs. So like I said, here is a box A. It's involved with many different well-separated pairs. These guys are all charging the same thing. Okay, what I want to remind you, though, is, in fact, this is making use of our packing lemma that we talked about last time. Remember, if you compute a well-separated pair decomposition, right, I think we observed this kind of idea last time, that if I go out to sort of a distance of, let's say if this is S, if I go out to a distance of 2 times S, and maybe to a distance of something like roughly 4 times S, okay, the boxes that this guy is going to charge are going to be boxes of roughly equal size that sort of overlap this region here. Okay? And you may remember from last time why this is the case, that you don't charge boxes that are very, very far away. And the reason is because when I was looking at the parent of this box and the parent of this box, they were already well separated. So you're only charging boxes in sort of a neighborhood region here. The number of such boxes is going to be, it's going to be some constant raised to the power of d, right? This is the number of boxes I have to worry about. So what I can do with that is I just have to fudge by little constants, right? If you remember, when we do the refinement, there was a little constant c. Let me see if I can go back and see this again. Yes, there was this constant c that we had to play with here. I'm going to make that constant a little bit higher. Okay? By making that constant a little bit higher, I can actually fudge this part of the thing so that the overcounting is not going to be an issue here. Okay. The second source of overcounting, though, comes from the fact that the height of the tree is involved here, right? As I go up to different levels, so let me go back to this guy. There is some spanning tree edges in here, right? And these spanning tree edges are being charged by this well-separated pair. But let's look at its parent, okay? When its parent is making charges, right? There are also spanning tree edges here. If I charge for a well-separated pair between this guy and some other parent, I'm also charging these nodes all over again. So the problem is that the same edges get charged at different scales throughout the tree. The lowest scale, the higher, and higher, right? So these scales keep working their way up. Okay, so multiple levels of the quad tree can charge the box. I have to think about, well, then how many levels could I have within my tree? Okay. So first thing you have to do is that constant that I was talking about before, you have to fudge it. And now it's not actually going to no longer be a constant. It's actually going to depend logarithmically on n and epsilon. Although to be honest with you, the 15 pages that we dealt with here actually worked very hard at getting rid of the n here. So at the end of the day, we actually have a term that depends on just log 1 over epsilon, with no influence on n. But in general, you have to consider how many levels there might be within the tree. And with a little bit of cleverness, you can get rid of the n term here, and it turns out to be just log 1 over epsilon. Okay. Okay. What's the execution time? Well, you have to build the original well-separated pair decomposition. S was a constant, so this is just S to the d, times n plus n log n. So that's just going to be n log n. We have to find the approximate closest pairs. Well, again, if you think about what we only had 1 over epsilon boxes. So if I look at all pairs of boxes, I get 1 over epsilon squared boxes that have to be considered. However, remember there was this little log factor that was sneaking in. I write log of n over epsilon here, but it's actually going to be just log 1 over epsilon when you get to the refined analysis. And so ignoring, I have a little tilde here, ignoring the logarithmic factors, the running time turns out to be about n over epsilon squared. Okay, good. So I'm just about at the end here. So in summary, and how are we doing here? Okay, not too bad. In summary, we have shown that we can build Euclidean minimum spanning trees by the standard, well-separated pair decomposition algorithm. And in fact, an interesting question would be, if someone were to ask me what algorithm I would use for building, well-separated pairs, I somehow suspect that I would probably use something that's based upon well-separated pair decompositions and some technique for coming up with, approximations. I don't know if I would use exactly this algorithm here, but I think some variant of this algorithm is actually a pretty reasonable one to use. We also talked about the fact, though, that there is this other algorithm. And by the way, this other algorithm is not particularly complicated, right? If you think about it, there's just a quad tree, there's a well-separated pair decomposition, there's a breadth first decomposition, and then you find a closest pair, right? I think I could code all this stuff up, and I'm not a very good programmer, okay? So I think that this is actually, a reasonably good algorithm. How practical it is, I'm not quite sure. The analysis, is relatively complicated, and, whether there's some way of making the algorithm, or at least the analysis somehow, yes, fit with the algorithm simplicity, I'm not quite sure. But the algorithm itself is simple and deterministic, just quad trees and well-separated pairs. The cool thing is the epsilon factors no longer depend on dimension. Okay? And you might say, hey, great, I'm in machine learning. I've got a 100-dimensional point set. I can now use your algorithm to compute minimum spanning trees. The epsilon terms don't depend on dimension, but there is still a hidden term that depends like 2 to the d. So the running time is more like this. Okay? So the good news is I can deal with very small values of epsilon in higher dimensional spaces, but you still cannot deal with very high dimensional spaces, right? And anything that's based upon a quad tree is going to have this 2 to the d factor, because this is just a problem with quad trees. Anytime you have any kind of locality, as soon as you have to look at your neighbors, you're going to have 2 to the d or 3 to the d or something like this neighbors. So you're not going to avoid that dependence on epsilon. But nonetheless, I think that for moderate dimensions, if you have a data set in dimensions maybe from 2 to 10, I suspect that this algorithm may very well be practical. I should mention, by the way, that this 2 to the d is sort of an upper bound. It may show up or it may not show up. It kind of depends on the intrinsic dimensionality of your data set. But it's not an intrinsic part of the algorithm. Yes. Okay, so let me get back to the caveats. I said earlier that to minimize the spanning tree means you minimize the weight of the spanning tree. Okay? This is not the only thing you might think of minimizing. And I'll pose a problem to you now. Let me tell you something about minimum spanning trees, which is actually quite nice. So here's a basic fact. Suppose I want to compute the following. Given points, let's say x and y, find the path that minimizes the length of the maximum weight edge on the path. Right? Usually when you think of computing shortest paths, usually what you compute is the sum of the edge lengths, right? If I have various, edges like this, I don't know, right? The cost of getting from x to y is going to be the sum of all these lengths here, okay? But what I want to imagine is suppose you're not trying to minimize the sum of edge lengths, you're just trying to minimize the maximum edge length. So maybe I've got another path here which uses nothing but very short edges, even though this path might be much longer, okay? From the perspective of minimizing maximum weight, this is the preferred path here. Now, by the way, this is a standard homework question in algorithms classes, right? How do you design an algorithm that minimizes this thing? You could modify Dijkstra's algorithm, okay, so that instead of doing sum, it does min. But it turns out the algorithm you get in that case is exactly the same as Prim's algorithm. In other words, the minimum spanning tree is the shortest path graph under this particular metric, okay? So one way in which to talk about, let's say, the minimum spanning tree is I would like to compute a graph that approximates what I would call the bottleneck distance. That is, the distance that minimizes the shortest path. Okay? The problem is, while Vijay's algorithm succeeds in minimizing achieving an epsilon approximation to this, Callahan and Kasaraju's algorithm achieves basically an approximation to the bottleneck distance. Their old algorithm and their new algorithm do this. Our algorithm does not do this. Our algorithm does not give you an epsilon approximation to the bottleneck distance. Okay? And the reason for that is because our errors may not be functions of just the edge lengths alone. Every now and then we could introduce an edge that is actually much larger than the actual, the edge itself. And that just has to do with the nature of the algorithm. If you can solve this problem, well, I can tell you there are at least two people in this world that would be very interested with it. Sunil and I would be very interested because we thought quite a bit about whether we could improve this result. And we have no idea of how to do this. It seems to be intrinsic to our method. So this is sort of the good news and bad news. And as I said over here, the big O hides constant factors that grow exponentially with dimension. Although they don't involve epsilon, they still are exponential in dimension. And that, again, obviously getting rid of that would be very interesting. But I somehow suspect that's going to be either very hard, if not impossible to do, without going back to these things that just estimate weight. I think it'll be very difficult to actually get the entire spanning tree, all the edges, without some kind of dependence, at least with respect to, like I said, some factors that grow exponentially with dimension. And folks, I think that is all. Yes, okay. I've been saying thank you. Merci, thank you. I've come up with now, okay, muchas gracias. So, yes, thank you very much then for your attention. And I'll be happy to answer any questions that you have. Yes?
Do you think that there's some more general technique there in this paper? It seems like it seems to be some kind of lazy well-separated pair decomposition, right? That you try to generate the pairs, the epsilon pairs on demand.
Yeah, that's a very nice observation. I hadn't thought about that, but you're absolutely right. In other words, what we do is we compute a coarse, well-separated pair decomposition, and then we kind of refine it down to the point where we sort of need it. And I like that suggestion of kind of a lazy well-separated pair decomposition. There may be other applications of well-separated pair decompositions where you try to do something like this. You start at a coarse level because it's very, very concise, and then you as much as you sort of have to refine. That sounds like a research grant. It's like, hey, here's a general class of, of optimization problems using well-separated pairs. Yeah, that sounds like a very nice observation. So no, I haven't thought about it. You should think about it quickly because now I'm going to go back and tell one of my students to think about it. Yeah. Yes, nice question. Other questions? Okay. Well, in that case, muchas gracias. Thank you very much for your attention.